Hey guys, so today's lesson is on electron affinity and it's going to be on electronegativity. So we're going to do two trends today. So far we've looked at a couple of big trends. So the first one we looked at was atomic radius, and the second one that we just looked at was ionization energy. Well, that includes IE1, IE2, IE3. So let's review, I guess. And ionization energy means the amount of energy it requires to remove electrons from an atom. And we said that as you move down the group, it gets easier and easier. So the amount of energy required will be less and less. So it will be decreasing. However, when you go across, theoretically or generally, as it increases, it gets harder and harder because the atom is getting smaller. So therefore, you're fighting with a stronger nuclear force. However, the increasing of ionization energy was not gradual, because you'll also have to take stability into account. So if you remove an electron off somebody who's unstable, but it becomes stable, well, you know what? The amount of energy will be low. It'll be easier. But however, if an atom is already stable and you're trying to take an electron away, you can bet your bottom dollar it's going to be harder, and you better bring lots of energy with you. So that was ionization energy. Now, what we're going to talk about now is called electron affinity. This is sort of the opposite of ionization energy, but you can't really say it's the opposite because you're not really talking about the same thing or the opposite thing. The process here is kinda, but what you're doing here is that you're adding electrons this time. You're adding electron to an atom. So let's say you have some sort of atom X and you're adding electron to it. Obviously, you become an anion. Now, would the atom like that? I mean, if the atom becomes stable by doing that, oh, trust me, you're going to get lots of energy as an output. You'll release lots of energy. Lots of energy. You release lots of energy. If you put an electron towards an atom and the atom becomes stable from it. Okay? So, let's take a look at the trends regarding electron affinity. First of all, you need to understand what type of atoms love to gain electron. That's right. It's these guys right here. Whoa, hold on. These guys right here. Okay? Noble gas doesn't want to gain. It doesn't even want to lose. It doesn't want to do anything because they're already so stable and happy. But not these guys. Oh, these guys are desperate for one electron, because if you were to give them one more electron, they look like these guys. We know that. And because of that, they release lots of energy when you give them that one more electron. Okay? Nature favors exothermic, meaning that the releasement of energy is what nature's favor. Anyway, we'll talk more about that when we get to topic 5. But in the meantime, the trend here is this. The more likelihood an atom gains an electron, the more energy it will release. Now, just by saying that, you need to do this. You need to ignore the noble gas because noble gas obviously don't come into play. So going this way obviously is increasing because nobody, if you think about it, would love to gain electron than fluorine. Nobody is small enough to gain electron than fluorine. It's almost like fluorine is so close to the nucleus because it has only 2 energy level that when you introduce an electron to it, it will just eat it up right away, quickly. Versus, let's say, astatine. Check out astatine. This guy is going to have a lot of energy levels. In fact, I can tell you right now, it has 5 energy levels. Okay? If you were to introduce an electron to astatine, he'll take it, definitely, because when he takes it, he looks like this guy. Okay, he looks like radon. But is he more willing or less willing to take that electron compared to fluorine? Because fluorine is definitely closer to the nucleus. Astatine is 5 levels away. Lots of shielding. So what can you say about going down the group? Well, it's going to be decreasing. Okay? You're not going to get as much energy, when your atom gets bigger due to the amount of shielding. You're going to get more and more energy as you approaches the nonmetals, because those guys love to gain electrons. Okay? The more that you want to gain electron, the more willing that you are able to take in this electron, the more energy you're going to release. Hence, you're going to have a high electron affinity. Okay? So hopefully you kind of understand how that works. Okay? It's really not that difficult, I hope. Anyway, we're going to move on. Okay? This is our 3rd trend. We're going to look into our 4th trend. So let's move into our 4th trend. The 4th trend is called electronegativity. Now, if anything, this is probably the most important trend out of them all. Okay? The way that this is determined is actually based on atomic radius, ionization energy, and electron affinity all put together. Okay? Electronegativity. Now, what is that? Well, what is this? Very simple. It's basically the overall tendency of an atom to attract electrons. Okay, the overall tendency of an atom to attract electrons. Basically, how much do you love electrons? Now, why is this important? It's important because later on in topic 4, we're going to talk about bonding. And there are different types of bond. There's ionic bond, there's covalent bond, and you're going to be introduced to something known as intermolecular forces, which is interaction, or even, you can even say weak bonds, between 2 compounds. Now, the type of bond that exists between 2 atoms is dictated by the difference in their electronegativity. Let me say that one more time. Okay? The type of bond that exists between 2 atoms is solely dictated by their differences in electronegativity. Now, don't worry if you don't understand it now. No need to worry if you don't understand it now, because when we get to topic 4, I will tell you exactly what that means and how to determine if 2 things were to come together, are they going to bond ionically or covalently? If they are covalently, is it going to be polar or non-polar covalent? Now that's That's a good question. But you don't need to worry about that question right now. All you need to know, of course, is the trend. Which element is the most electronegative? Again, just like electron affinity, we're gonna black out these guys. Let's black them out because they don't play a role. Let's ignore those noble gas. Okay? Because the overall tendency of an atom to attract electron, well, these guys don't want to attract nothing. So by putting them there, it will just mess up the trend. So here's the trend. Or here's something to memorize. Just something to memorize. Fluorine is the most electronegative element of them all. You just need to memorize that. Fluorine, there's no atoms right here. No atoms who would love electron more than fluorine. We saw how much energy it releases when he gains an electron. Well, guess what? That's because he loves electron. I like to I guess abbreviate fluorine as a she sometimes because it sounds like a female name, fluorine. Such a nice name. I would love to name my daughter one day Fluorine. Well, as you move across the periodic table, obviously, electronegativity increases. Okay? Knowing that the fact that fluorine is the most electronegative. So I guess if you go down the family, it decreases. Okay? Now, the reasoning is quite simple here. Quite simple. Fluorine being, I guess, in this case, the smallest of the group. Okay? I guess in terms of ionization energy, it's also the smallest of the group. It doesn't want to lose electron, not even a bit. Okay? Of course, we're still ignoring those noble gas. Just looking at this picture right here, fluorine doesn't want to lose electron. Electron affinity, a lot of energy is being released if you drop an electron to fluorine. All that put together gives fluorine an identity where he loves to be around electron. He loves to attract electron. He loves to, he loves his own electron. He's very small, so therefore the attractiveness towards electron because of the nucleus is going to be high. It's going to be strong. Such a small atom. Hence, F is the most electronegative. Now, that is something that you might want to memorize, okay? Because by knowing that, you know if you were comparing electronegativity from one atom to another, you sort of have a way to gauge, okay? Later on, I will give you another periodic table, okay? This periodic table outlines the electronegative value for each of these elements. It's actually a scale from 0 to 4. Fluorine actually has an electronegative value of 4.0. Okay? So there is no element here that will be greater than 4.0. That is just obviously something that we will look upon. Just in case if you're wondering, oxygen is actually 3.5, something like hydrogen is like 2.1. Okay, so these numbers are numbers, that indicate their tendency of attracting electrons or just, loving their own electron. Yeah. Anyway, there's also something called electropositivity, but electron-positive is not something that you'll hear people talk about at all, okay? So if electronegative is the overall tendency for an atom to attract electron, I guess electropositivity is the overall tendency of an atom to, I guess, lose electron, not attracting electron, okay? Not really wanting electron. I guess the latter will make the most sense, you know. I don't want electron. Get that electron away from me. So if I were to ask you a question from this periodic table, which element would say that? Which element would say, don't give me that electron, take that electron away, or else I'll get mad? I hope your answer will be francium. So francium will be the most electropositive. The reason why we don't talk about electropositive is because I guess there's really no point. Okay? There's really no point. There's nothing that comes out of it. Remember, electronegative will dictate the type of bond that two atoms can make. Electropositive doesn't do that. All right. So those are the main trends: atomic radius, ionization energy, electron affinity, and here, electronegativity. I have one more trend, okay, that I will introduce you to the next day. It's called ionic radius. Again, yeah, that's right, we're looking at size again, but this time we're going to look at size of ions. We're going to compare ions to ions. We're going to compare atoms to ions, or maybe different atoms with different ions. That's certainly interesting to know. All right, let's call it now. Bye, guys.